Okay, this is a quick introduction to the purpose of vectors. Um, Vector is a value that has a quantity and a direction. Scalars are values that just have a quantity and no direction at all. And vectors are often used for things like displacement, acceleration, velocities, forces in mechanics. But they can be used in other areas as well of mathematics. They actually use vector mathematics in quite a lot of business calculations as well. And vectors can also describe more than just two directions, they can describe three. So we'll talk about a little bit into these in a few moments. Let's start off with just basically what a vector is. So if I have a set of axes, a vector describes movement on the axes. It can describe a location, but it can also describe the relative movement between two places as well. Now we normally have axes x and y, and in vector form the x direction is the I vector, and the little hat over it says this vector is a pointer vector. It has no actual size apart from 1. So if you see a hat on it, I hat is a length 1 and a direction. Okay, so I could actually write this following. I could draw a vector v, and I've got 3, 2. So there's my vector v. Vectors normally have an arrow over the top of them, or they can, in books they'll often have a vector written with bold. Some people write it with a tilde. You'll see that quite a lot in America. Lots of engineers will use an actual arrow, saying it's a value with a direction. This vector, same as with x and y, we go in the x direction first, so it's 3 in the x direction, which is the I pointer, and 2 in the vertical direction, the j direction. And this is the algebraic form. Quite a lot of people like it and use it. When I come to mechanics though, I actually prefer a column form that you'll probably be familiar with from translations. And that is where you have the x and y components listed one above the other. Now, the reason I like this is if I was trying to do a displacement calculation using a velocity and a time, that's this normal formula we'd use. The vector version, the displacement is a vector, the velocity is a vector, and t is a scalar. And if I actually wanted to get the results out, I could find the position x and y using a vector calculation of 5 and 2 times t. The equivalent would be an xi plus yj equals 5i plus 2j, and in brackets t. It just, to my eye, the column vectors seems a little bit nicer. So we've got a vector, and let's just put a couple of quick vectors in and we'll do some bits with them. So we've got that first vector, which is 3, 2. Let's do a vector w, which is that one. Scroll down a little bit, I'll take the titles out of the way. Sorry, I'm not colouring the video, but when it comes back to the notes, I'll have colourised some of this. So W does that, and vector here, and vector W, let's call it vector U. Don't have to go into X, Y, Z because of the coordinates being X, Y, Z. So W could write as a vector either as minus 1, 3, minus 1 in the I direction, plus 3 in the J direction. And in the algebraic form, it doesn't matter which way around the I's and J components are. So some people will actually do 3J minus 1I or minus I. It's all fine. if you use a column form, the format is always -1, 3. You must get both values. Okay. Vector U. This one is in for a very important reason in a few minutes. So we've got -2i and -4j. And that vector, you can put them in brackets. We'll have a, but let's put it as -2, -4. Okay, so we've got 3 example vectors. We're going to go through and do bits and pieces with them as we go through. The first obvious thing is if we turn around and turn them into right angle triangles by dropping the perpendicular. Actually, that last one is probably, no, let's leave it now. If we drop these down, I and j, traditionally, because they're x and y, are going to be at right angles. Right angles and right angles. So that actually means we've got right angle triangles, and with the right angle triangles, that means we can find a length. The length along this side, sometimes written just as v without the arrow, or the modulus of v, with modulus around it, comes from doing Pythagoras. So Pythagoras theorem, what happens is the length along the side, v squared, is equal to the x coordinate, 3 squared plus 2 squared. So v is the square root of 9 plus 4, square root of 13. In M1 decimal, calculator decimal, 3 significant figures, good values. So let's do the modulus of, write it as modulus as well. So the modulus of w is going to be the square root, and this is something you should remember from being told in when you were doing Pythagoras originally. Anytime you've got a negative number as a coordinate and you're using Pythagoras to work out what's happening, put it on in brackets. Calculators have 2 negatives. They've got a negative property of a number and a negative subtract sign. The subtract sign I've got no problem with, but the negative property number, it treats it as a subtract. So it squares first and then puts the minus on it. So to make sure that you put the minus first, you put the minus in a bracket and square it. And then we add on 3 squared. So this is the square root of 10. And the length of u is equal to the square root of -2 squared plus -4 squared. That is the square root of 20, which is 2 square root 5. So that's us calculating the length. We can also measure the angle from the horizontal axis. The angle in there. And that's called the argument. That's when it's arg. And the arg of the vector v is the angle. And that angle comes from doing, we've got an opposite and an adjacent. So that's a tangent. So it's from doing the arctangent, or tan to the -1, of our opposite, which is the j component, over the y component, over the x component. So shift tan of 2/5 is gradient of 21.8 degrees. In mechanics, that would probably come up as being in degrees. P4, they'd probably go for the degrees as well. They're less likely to use radians for this, but read the question carefully. If the question's using radians, give the answer in radians. So the arg of W is the tan minus 1. So I'm using tan minus 1 rather than arg tan this time, of our y part divided by our x component. So our shift 10 of 3 divided by minus 1, and that's gives me a minus 71.5 degrees. Now, if you actually think about what that's saying, that's pointing down this way. It's exactly the opposite direction. And that's why you have to be careful. When the x component is negative, you often get the wrong angle being given. So to correct for it, we need to add 180 degrees to bring it all the way back round to the right direction. Okay. So minus 71, and then we add on 180, and we get 108.4 degrees. So because this is negative x and positive y, we know it's going up from this axis, and we know it's going back from it, from that point. So we need to correct for the mistake of the cancelling going on in here. Same thing happens with the last one. We get a section, and we get the arg of u, the argument of the vector u is the arctangent of minus 4 over minus 2. Which is 63.4 degrees. But this distance to root 5 at 64 degrees, at 63.4 degrees, goes in that direction. And that's the incorrect vector. The vector goes in the opposite direction. So we need to add or subtract 180 degrees. Check the range in the question. They may actually give you a range. And if there's nothing stated, I would try and always keep it positive. So add the 180. So I'd say an angle of 243.4 degrees. Okay, so this is the first video on the introduction. I'll make separate ones.